I need to practice one. Okay, let's go over what these variables mean. Okay, first thing, magnetic field due to a solenoid. Anybody remember what a solenoid is from the notes?
Yeah.
Electromagnet. So it's a coil of wires, like this, that has a current running through it, that acts like a magnet when there's a current running through it. So it's a magnet when the electricity is on, it is not a magnet when it's off. So the magnetic field generated by one of those things equals the mu naught. Anybody remember what that is?
Yes.
Alright.
It's a constant.
It's a constant. It's 4 pi times 10 to the negative 7th.
But the pi's cancel out.
Not in this
In
one.
that case.
Pi's do not cancel out. This one is not divided by 2 pi. Okay.
Go to look next time.
I, what's I going to be?
Current.
Current, measured in amps. What's N?
Number
Number of turns, number of loops. L is the length, and when we say the length, we mean the length when it's all coiled up, not when it's stretched out. Does that make sense, everybody?
Yes.
Yes.
Yes. Yes, sir.
See?
Okay. Current in a transformer is the same thing we did as voltage in a transformer. We did it yesterday. Instead, we're finding how the current changes. And in a transformer, when the voltage goes up, the current goes down. So yesterday, the voltage and the number of turns were directly proportional. Now, the current and the number of turns are inversely proportional. So the number of turns goes up from one side to the other, the current goes down. Does that make sense to everybody? Okay. Next one is power lost in electricity transmission. And it's P equals the current squared times the resistance. So when you transfer electricity from like the power station to school, for example, you lose some energy due to the resistance of the wire. Does that make sense to everybody? And transformers are there to minimize that. And power produced at the generator is just the current times the voltage. Alright, so this is the power lost ones are kind of the most confusing, but they're still really not that difficult today. And you guys are going to have a group quiz tomorrow over all this. Shocking. You're not going to have a snow day tomorrow.
Length is always in meters, right?
Length is always in meters. Okay. I don't think we're going to have anything tomorrow. Yes. We're probably certainly not going to have a snow day. Maybe a 2-hour delay, but probably not. Oh, tomorrow. Yeah, I wouldn't bank on anything. Okay. Shh, quiet, guys. Alright, number 1. A solenoid has 530 turns of wire and a length of 16 centimeters.
Something for Gabe from this spot.
You're supposed to clean this up, apparently.
I'm not
Ew.
touching.
What
What is it?
What is
I
that?
don't know, it's like white and stuff.
Okay. I have no idea what that was, but he's supposed to clean it.
Does it look edible?
Alright. Okay. Sorry, we got distracted there. Has length of 16 centimeters. If the current in the wire is 5.9 amps, what is the magnetic field generated? Alright, so this one we just use B equals mu naught I N over L. So what's mu naught?
4 pi times 10 to the negative 7.
4 pi times 10 to the negative 7. What is the current?
5.9.
5.9 amps. How many turns are there in the wire?
530.
530. And what's the length of the solenoid?
0.016 meters.
Remember, you gotta convert the 16 centimeters to meters. So divide by 100. And what is the magnetic field? .02.
I think. I'll double started before you did it.
And that unit for that is Teslas.
I have 0.02. Yay!
It's not. 10 to the negative 7th is a really small number.
You're dividing by a really small number.
10 to the negative 7th is way smaller than
Do
0.16.
radians matter?
Radians do not matter in this topic. Alright, can I erase this?
Oh man.
So what was the answer? What are you having your
0.02 Teslas.
You guys done?
Yeah.
Okay. Next one. A transformer is used to step up the voltage to send electricity through power lines. The primary coil has 13 turns and the secondary coil has 4,950 turns. The generator producing electricity.
That's awkward.
You're knocking on the table? Sorry. Okay, generator producing electricity produces 75 amps at 240 volts. And the resistance of the power lines is 0.5 ohms. How much power is lost when the voltage is not stepped up, and how much power is lost when it is? So we're going to have two answers here. When we do this one, I'm going to find one thing that's, we don't need to have either of the answers just because it's interesting to compare. Alright, so first we're going to do it without the transformer, without being stepped up. Okay, so first thing we're going to find is the power from the generator. So power equals IV when it's coming from the generator. And what's the current?
75.
75 amps. And what's the voltage?
240.
240 volts. So what is the power equal that's produced at the generator?
18,000.
18,000. What's the unit for power? Watts. Alright. So 18,000 watts produced at the generator. Then we have the amount lost is P equals I squared R. So the power lost is 75 amps squared. And what's the resistance in the wire?
0.5.
0.5 ohms. And what does that equal?
2,812.5.
2,000 what?
812.5.
2,812.5 watts. So what this means, that's how much power is lost when it's transmitted by, somebody at the door?
Yeah.
No.
No.
Okay. For every 18,000 watts of power generated, 2,800 are lost. So that's a pretty big portion of it. So that's without using a transformer. Now with the transformer, we gotta figure out the current in the secondary coil, and then use that current with P equals I squared R to find the power lost.
Don't start that yet.
Okay, so we're going to use current in the secondary times number of coils in the secondary equals current in the primary times number of coils in the primary. So current in the secondary is what we're looking for. How many turns are in the secondary coil?
4,950.
4,950 turns. What's the current in the primary?
75.
75 amps. And what's the number of turns in the primary?
13.
So 13 turns. So the current in the secondary equals 75 times 13 divided by 4,950. So it's going to be pretty small.
0.20.
So 0.20 amps. And now we use P equals I squared R to find the power lost. So it equals 0.20 amps squared times 0.5 ohms And what does the power loss end up equaling?
0.02.
What is it?
0.02.
Okay, so 0.02 watts. So for every 18,000 generated with the transformer, only 0.02 watts is lost instead of 2,000. So you see how that makes a big difference? So that's one of the main reasons why AC current is used pretty much everywhere, is because when you transmit it from the power station to someone's house or to their business, you lose significantly less energy. However, all the stuff that almost everything in your house ends up being converted to direct current. So like your TV, most of your the microwave, anything that has electronics in it ends up being converted to direct current by something called a diode. So even though almost everything you use uses direct current, it's so much easier to transmit alternating current that's what's used. Brian, you have a question?
Do they use DC in Europe?
Some places do use DC. I don't know what does. I believe some countries in Europe do use DC.
Like, why do you buy like a converter or something?
You have to. They all have different They all have different voltages.
Oh.
I know that. As far as DC, I don't know. I should know this. I want to say I do think some countries in Europe use DC, but in the United States we use AC.
Right.
And it's because it's less energy is lost when it's transferred. Okay. Can I erase this? Or, Michael?
So, do you actually need to find the 18,000 part?
Don't need to find the 18,000 part. That was just so we had something to compare it to.
Okay.
In this next problem, it's very similar, and we're going to need to find the 18,000 anyway. So.
Okay.
I'm going to look up the DC current thing. It's going to bother me.
So, how's everyone doing today?
Hey, CJ.
What's up, CJ?
Mr. Kent is looking something up right now.
Here we go, Knights.
The one thing he doesn't
It's
Hey.
going out.
Roll Tide.
No, not at all.
Follow me on Twitter.
Um, Very few countries use DC is what I'm finding here. So I'll have more information later. But
Mikey. This is my friend Mikey. He sleeps in class.
It's not true.
He's walking past you now.
all right. Anyway, sorry about that. All right. Answer your question, Brian. No significant countries use DC current.
So it's just
It's just the voltage is different.
That's what
Like, so I think I saw Algeria use DC current or something like that. Like,
That's significant.
not me. I could be wrong on that too.
Algerians just got disgraced.
All right. Okay. Anyway, so no, Europe uses DC current. The voltage is just different.
Alright.
Okay. All right. So number 3. A transformer is used to step up the voltage to send electricity through power lines. Primary coil has 10 turns. Secondary has 3,400. The generator producing the electricity produces 50 amps at 140 volts, and the resistance of the power lines is 1.2 ohms. What is the
Wow.
So many distractions. Come on, man. Don't
Okay.
look for the camera.
Okay. Okay. It's been a very interrupted day here, hasn't it? All right. What is the percentage of the power loss when the voltage is stepped up, and when it isn't? Okay. So we're gonna have to find the total, and then find the power lost. Divide the power lost by the total, and then multiply by 100 to get the percentage for each of them. Does that make sense, everybody? Okay. What is the? There's a toolbox over there looking for players. Alright, so to find the power produced at the generator, it's P equals IV. The power equals current. What's going to be the current in this one? 50 amps. And what's the voltage? 140 volts. Okay. So that our power ends up equaling 7,000 watts. So that's how many watts are produced at the generator. Now we do P equals I squared R to find the power lost. So power equals 50 amps. And what's the resistance? 1.2 ohms. Oh, 50 amps squared. So the power equals 3,000, is that right?
Yeah.
3,000 watts. So now to find the percentage of power lost, for every 7,000, 3,000 is lost, so 3,000 watts divided by 7,000 watts times 100% equals 42 point something percent.
Let's find out. 42.32.
42.6%.
Yes.
Okay. Any questions on what we did there? Okay. So with the transformer, we're going to start with the transformer equation for current. And we'll look for secondary, current in the secondary one. How many turns are in the secondary one?
3,400.
3,400 equals current in the primary, which was 50. And what's the number of turns in the primary? 10. Current in the secondary is going to be 500 divided by 3,400, so 0.15. 0.15 amps. Now I do P equals I squared R. 0.15 amps quantity squared times, that should be no ohms there. What's the resistance? 1.2? So what's the power lost when it is gone through the transformer? 0.027? Alright, so that's a very tiny power loss. So now I do that number divided by 7,000 times 100%. So 0.027 watts divided by 7,000 watts times 100%. And what's the percentage? It should be a really small number.
3.85 times 10 to the
3.9 times 10 negative 4?
What?
Yeah.
I got 4.3.
So 3.9 times 10 negative 4th percent is lost. So can you guys see why we use AC currents in order to avoid power losses? Because without AC current we can't use transformers. And without transformers we'd have to lose significantly more power and electricity or energy than we would if we did. And one of the things that you guys heard of people talk about like the smart energy grid and things like that. One of the goals of that is to reduce the distances between power stations and reduce the resistances between power stations and like what needs it. So if you reduce this number, in either case you lose a lot less energy. And one of the things, this is kind of a theoretical thing, they have these, but not at temperatures that are acceptable. Have you guys ever heard of something called a superconductor? A superconductor is something that has zero resistance. So if we had zero resistance, we'd lose no electricity due to when we transmitted power, which would save a lot of energy. Problem with superconductors is they only exist at very low temperatures, like 200 Kelvin or so, I think, is the warmest one, which is negative 73 Celsius, which is very cold and not going to be able to be practical for power lines. But they're trying to find superconductors that work at higher temperatures.
When you say that the energy or the power is lost, like, is it just not all of it is used, or like where does it go?
It turns into heat.
Okay.
So the power lost here turns into warm the power lines. That's one of the reasons birds like to sit in power lines in the winter, especially because they're warm.
Okay.
Any other questions about this?
We're
Michael?
gonna be doing number 4.
You guys are doing number 4 on your own.
What's
What
that
is the
E, the minus?
Oh, the 2.19 times 10 to the negative second.
That is what it is?
That's just the program I use to make these, so they can be variable. It doesn't do exponent, it doesn't do
Okay.
scientific notation. Normally it does it like that.
So it's negative 2, not
Any other questions?
2.19 times 10 to the negative 7.
Yep. Alright, you guys finish this worksheet. Rest of class here. I will give